Good afternoon, all, and thank you so much for joining our fourth session on our use of low-cost sensor for air quality monitoring in South Asia virtual training series. And before we get started, I would like to introduce Health Effects Institute. So, Health Effects Institute is a not-for-profit research organization based in US, and we work on three different verticals: energy, environment, health, and global initiatives. And under our global initiative program, we are currently active in East Africa, South Asia, and we do both research and capacity strengthening activities there. And in South Asia, we have been conducting those capacity strengthening activities both in person and on virtual mode on air pollution, on different topics under air pollution and health. And this year, we have planned for a five-part training series on use of low-cost sensor for air quality monitoring. Already, the three sessions on this training series have been completed, and the materials, both the slides and the recordings, are available on our website. I can share the link with you in the chat box. The first session was on the overview of low-cost sensor by Dr. Srikanth Vakasala, where he provided what are all the available sensor technologies, its applications, limitation, and he also walked us through different components of sensor. And the second session was on sighting and network design by Dr. Sophia Rao and by Dr. Dio Okure, where the idea of that session was to provide both regional and national, like regional and global perspective on sighting and network design. And the third session was by Dr. Nimit Kothani, where he brought how to develop a low-cost sensor network right from scratch, even to and maintaining such a large low-cost sensor network. He walked us through the entire steps in this process. And today we have Dr. Emil Varghese with us to present on how to manage the collected data and how we can analyze the data that we are collecting through this sensor network. I would like to give a brief introduction to Emil before we get started. Emil, uh, she come. She is a senior associate in air quality sector at Center for Study of Science, Technology and Policy, CSTEP, which is a leading policy think tank in India. As an early career researcher, she holds a master's MTech in environmental engineering and PhD from Indian Institute of Technology, Madras. And her research focused on role of bioaerosol in climate and ecosystem health interaction in Indian tropical region. And here at CSTEP, she leads the sensor evaluation at India Sensor Evaluation and Training Inset facility. She also operated a multi-pollutant low-cost sensor network in Bangalore, co-led the Air Lab Microsensor Challenge 2025 India site, which has contributed extensively to development of an air quality data management system for improving sensor data reliability. She has been actively involved in conducting several training sessions on air quality monitoring and sensor data analysis for the State Pollution Control Board. She has also contributed to international conferences by serving on the technical planning committees, including for the one on air sensors International Conference 2025, and also on the organizing committee of IGAC, ICACGP ECR online conference, and she's also currently a co-chair for IGAC Early Career Short Course 2026 organizing committee. We are very glad to have you, Emil, here today because on the last sessions there was like lot of questions on data credibility, how to use this data for better purposes. So we are very glad to have you here, and over to you.
Yeah, thank you, Abhinay, and thank you, HEI, for inviting me to this session. So I'll quickly share my screen. Yeah, hope the screen is visible to everyone.
Yes, it is visible.
Yeah, sure. So first of all, before jumping into the air quality data management and analysis part, I'll just introduce about our organization, that is Center for Study of Science, Technology and Policy. So we are one of India's leading think tanks with a mission to enrich policy making with innovative approaches using science and technology. And we mainly work in areas like clean energy transition, clean air for all, sustainable secure future, digital transformations, and strategic initiatives. We have been having research for 20 plus years, and we have published nearly 150 plus research publications and nearly 15 plus tools powering action nationwide. Firstly, let me introduce two particular sectors in CSTEP, which has mainly worked on this air quality data management and analysis. So I mainly come from the air quality sector, and we work closely with the state and central pollution control boards at identifying pollution sources through emission inventory and source apportionment studies. We have used loco sensor networks. Then we have a PM chemical characterization using high-end instruments. We work in air quality modeling using ChemX, and also we are mainly actively participating in the capacity building for state and pollution control boards. At the same time, I have a support from the artificial intelligence and digital platforms, that the AIDP sector in CSTEP, which is leading the development of certain decision-making tools and information portals, such as a source apportionment tools, air quality data management system, which we'll be talking in detail in the coming slides. Then other works from AIDP sector is the rooftop solar explorer, climate change risk assessments, etc. So in as we know that there are certain questions like what is the data reliability for the sensors, because the main concern when we look into the sensors is that the sensors has a cross sensitivity across different different pollutants. At the same time, it gets affected by the meteorological conditions. So in the world perspective, we had nearly that AQ spec, which is looking into the sensor evaluations, which is under the South Coast AQMD, and Afreset Ghana, which was working on the sensor evaluations in Africa. So, taking models from this, in December 2023, we established the India Sensor Evaluation and Training Facility as an independent standardized testing for air sensors in India. So we have reference grade instruments for, as you see here, we have for PM2.5, PM10 BAMs. Then for looking into the optical particle counters, we have the FIDAS. Then you have for the gases, the NO2, ozone, CO, and SO2 monitors. We have an automatic weather station for looking into the meteorological parameters. And additionally, we also look into the PM chemical composition that can affect the sensors through certain instruments like for black carbon measurements, we have the ethylometer. Then for real-time chemical characterization, we have the AQMS, for metal characterization, etc. So these instruments are deployed in our Interset facility in Bangalore, in our CSTEP campus. And based on this, using these instruments, we have carried out two sensor evaluations, one particularly for the sensor manufacturers in India. And this was a long-term evaluation, which spanned from January 2024 to January 2025. And phase two sensor evaluation, it is in partnership with the AirLab Microsensor Challenge 2025, where we partnered with AirParif in France and Afriset in Ghana, where we were looking into different sensor manufacturers globally, what is their performance of the sensors. And in Indian side, we had 18 manufacturers who put up 3 sensor nodes each for a period of 4 months, looking into the sensor performance. So these are the works that we have carried out, and I'll now move on to the sensor data handling. First of all, we all know that once you have a sensor in hand, or when you purchase a sensor, the next step that everyone would be looking into is the collocation with reference instruments. And this collocation study mainly has two parts. That is, one, we will look into the performance evaluation, and the other part is the development of localized calibration models to improve the data accuracy. And once we have developed all these models and we are confirmed with the performance of the sensors, we move on to the sensor deployment, and then we look into the sensor network data analysis. Now I'll just focus more on the collocation, how we look into the sensor data. First of all, first of all, this is we need to know what are the different types of sensor data that we are handling. Particularly, if you know the type of sensor data you're handling, then that it exactly tells us what it actually represents. So here I'm taking an example or a proposal from Schneider et al. 2019 on different sensor data processing levels. So level 0 means it is a raw measurements. So here Schneider et al. 2019 is actually estimating as actually trying to compare the different satellite, like in satellite data we have different levels. So similarly, he is trying to compare it with these sensor data and assigning different level names here. So level 0 as raw measurements means if you have gas sensors, you are majority of us are using electrochemical sensors. So these electrochemical sensors has voltages for the working electrode and the auxiliary electrode. So these voltages corresponds to the level 0 or the raw measurements when it comes to the gas sensors. And when it comes to the particle sensors, it corresponds to the lights, it again corresponds to the voltage, or in the case of sensors which are working in Neflometer principle, or it can be the bint counts when it comes to the optical particle counters. Now, level 1 means it is like a factory calibration. That is, just you have the level 0 data, and then you are trying to convert into the specific units of that particular pollutant. Take an example like NO2. We just convert to microgram per meter cube or ppb from that voltage levels by just adding an additional factory calibration. And similarly, when it comes to the particle sensors, it is that the bint particle counts or the voltages corresponding to that light scattered in Neflometer, we just convert into the microgram per meter cube. And comes as the level 1 data. Now we have the level 2 data. Level 2 data here, what happens is we account into the cross interference of the different pollutants or the metrological parameters. Say in the case of gas sensors like NO2, there can be interference from the ozone sensor or from the CO sensors. So we look into this factor. At the same time, we look into the temperature and RH factors. Now there is when it comes to the PM, we look into mainly the temperature or RH factor, and then we convert it. Now there is two different things in level 2A and level 2B. Suppose you are using the localized or particular locations meteorological parameters, then that corresponds to the level 2B. Say that you are buying a sensor, putting it in Bangalore. Now, if you want to correct it with the Bangalore's temperature and RH conditions, as well as the cross interferences, then you are standing at the level 2B data. So that is the localized calibration data. Additionally, there can be other data sets which are not that commonly used currently, where you can build your own models. Say that you are considering other factors or proxies of certain measurements, and you can further improve your data qualities. So these are the different ways these are the different levels you can consider when you look at the sensor data. Generally, what happens is you may have access to the level 0 data, but that is not that is generally available from the manufacturers or the sensor integrators only as like on request. And then we may have access to the factory calibrated data which the manufacturers provide, or it can be the localized corrected data which you are yourself building by developing your own calibration models. So now when we look, when we know which are the different types of data we have, the first step that you need to look is how do we evaluate these sensors. Now, once we have collocated the sensors with reference instruments, the first step is data collection. Then comes data standardization, that is data cleaning, data processing, and performance evaluations. So I'll be discussing about these in detail in the coming slides. And another part of the collocation study is development of calibration models, that is collocating the sensors with the reference instruments, and then the data that you collected during the collocation study, you split the data into a training data set and a test data set. So people can split the data into 80-20, that is 80% of the data is the training data set for building your model, or it can be 70-30, that is 70% comes to the training data set. And then we develop the correction models using the training data and test the model performance using the test data, that is the remaining data from the training data set. And Another important thing we need to note here while we are developing calibration models is sometimes the model that can work in a particular season might not be efficient enough to work in another season. So periodically checking the model performance is very important when we look at the sensor data. And also there is aging of sensors that happens. So definitely the sensor performance also need to be checked while we are looking into the data performance. Now coming on to data collection from sensors. So here is a photograph of the inner side of the sensors. So you have the PM sensors like PM sensors which are placed outside that use here you have the for the plant towers, then you have some OPC sensors over here. Then there are certain gas sensors. So here it is examples from the alpha sense gas sensors. And then the data is available in through two forms, particularly for this particular device. That is through SIM card, and that is IoT based connection. And then you can store the data in the SD card. So what mainly happens is that when you have from sensor node has this SD card, and it gets stored, the files get stored as .csv files or .txt files, and this data file can be further used for analysis. Now, when the data is stored in the data transmission takes place through IoT SIM card or by connecting to Wi-Fi, then the data first moves to the manufacturer server, and then from the manufacturer server, either you can get the data by fetching the data through manufacturer API documents. You can just ping the API and get the data, or you can download the data from the manufacturer dashboard. And sometimes you can even visualize the data through the manufacturer dashboard. So once you have the data, if suppose you want to build your own calibration models, you want to have your own data analysis, then you have to fetch the data through the manufacturer API and then store in a database management system and do further analysis. Now, first of all, what's the need of data standardization? So the data that you collected in hand is say that it is say that you random say that you are in India and you want to take that data and the data is in UTCs. So now you have your reference instruments reporting the data in the Indian Standard Time Zone, and then your sensor data is being reported in the different time zone. So the first important thing that you need to make is to make your data to the local time zone. So if you are looking at India, you convert into IST, or if you are in Europe, you look into the CET conversions. Then another thing we need to notice is that when we have sensors from different manufacturers or certain manufacturers, the way they store the data through the manufacturer API is like they give just notations like P1 is equal to a value, P2, that is the next pollutant, is equal to some other value. So there you need to make sure that you're assigning proper parameters or proper names to it. Say that for PM 2.5, you have PM25, or PM10 means PM10. So that is called the standardization of parameter names. And then there comes the standardization of units. Sometimes your reference instruments are recording in ppbs, while your sensor is giving microgram per meter cube. Now, if you want to compare your sensor to your reference instrument, then definitely you have to, at this stage, you have to convert the units. So this becomes an important thing because sometimes you have CO's values in milligram per meter cube in one side. On the other side, your reference instrument is recording a ppm. So this need to be carefully done. And another thing here, when data standardization comes, is aggregated to 1 minute interval. That is, sometimes certain sensors can even transmit the data in 10-second interval. But in 10-second interval, there are high chances that you will be facing even the noises. So to eliminate this, we generally apply a 1 minute interval aggregation at the first standardization stage. And then we move on to a data cleaning stage. So ideally, when you have to evaluate the sensor data for a network, the first thing that you do is, if you have, say you have 1 month of data with you, the first step that you can do is remove the days with less than 75% data availability. As you generally USCP also recommends this, that if it is less than 75% data availability, then you cannot even consider for a daily average value. So remove the days which is having less than 75% data availability. Then another thing that you notice when you comes to the sensor data is you may face negative values. So because there might be some factory calibrations that have been applied, or say that sometimes you are noticing PM 2.5 as negative for 0.5 microgram per meter cube. That is ideally not a right value. and definitely you need to remove those negative values. Then you have a concern for the threshold values. Say the sensor can measure only till, say you have a PM sensor with you, and you can, the sensor can measure only till 1000 microgram per meter cube. But there are values that is there in the sensor data, which is showing 3000 microgram per meter cube, which is completely out of the threshold value which the sensor can detect. So such values we need to remove at this data cleaning stage. Then comes to the data processing step. So here data processing is, here we are doing a data processing to check the performance of the sensor to the how the performance of the sensor is towards the reference instruments. Now for that, the best things you can do is, one, for gases, if your reference instrument is reporting 1 minute averaged data, then you, for the sense, then you can aggregate or average your gas measurements from the sensor as well as the reference instrument to 15-minute averages, and then compare to each other. So you're not missing the sudden events that is occurring. Say that some truck has passed by and NO2 concentration has increased suddenly. So these things you are not missing it out. Now, majority of the reference instruments for PM, they measure it in 1 hour averages. Say you have a beta attenuation monitor BAMs with you for measuring PM 2.5 and PM 10. Then they will be majority of the reference instrument manufacturers, they do the 1 hour averaging for the measurements. So then you can even then you have to even if your sensor can report at 1 minute, to compare your sensor performance to the reference instrument, you will have to do a 1 hour averaging for the analysis. And every time, one important thing to be noted here is that whatever aggregation or averaging you are doing at any step, make sure you're considering a 75% data availability for averaging. Another important thing here is, during data processing, one of the errors that can happen is, say that I am considering my, I'm considering like average, when I'm averaging the data from say 10 to 11 hours, and I assign to 10 hours, and I call that 10 to 11 is in the starting of the hour. That is 10. That is something which I'm considering. Now, suppose say that someone else might say that, no, you cannot consider 10 to 11 as at 10. You must consider 10:30, which is the midpoint of that hour. And sometimes people may take it in a different way, that 10 to 11, assign it to the end of the hour, which is the 11 hours. So whether you're considering a backwards or the forward or the midpoint is something we need to have it while we are doing any data analysis. We need to ensure that we are following a particular convention throughout the analysis. And then once we have fixed on your analysis convention, then you move on to merging your sensor data with this reference data based on this based on the date and time. So once you are ready with your data analyzed, the first thing that you need to see is, say you have 5 sensors from a single manufacturer in your hand. Now, are all these 5 sensors actually representing, actually giving similar values or precise value to each other? Is the first step that you need to see in the sensor performance. So for that, there are different metrics that has been suggested by US EPA, as well as now in INTISET, we have also considered certain thresholds, which I'll be explaining in the later stages. So these threshold values or target values we can look into using different mathematical metrics. Before we jump to the mathematical metrics, the first and quick way we can check if the performance of sensor is precise to each other is just using a simple pair plot, as you could see here. So in Python, it's very in Python language, which is it's very easy to just plot a pair plot and see whether each of the sensors. So here, this is 2142, 2143, 2141. These are the names of different device IDs from a sensor, and you are just comparing whether they are precise to each other. That is, when you just compare 2141 to 2143, ideally it should have been through a 1:1 line if they are precise to each other. Or if there is this can be just visually seen using a pair plot. Now, to additionally to see not just with visualization, but with certain metrics, we have different metrics like Pearson correlation coefficient R, coefficient of determination R squared, then standard deviation, and coefficient of variation. So this is these formulas for standard deviation, and this that is SD, and coefficient of variation CV. These formulas are being taken from the adopted from the US EPA guidelines for the for the different target values. So here we are considering that, say that you would need to look the SD of 1 hour average sensor PM concentration. Then N corresponds to number of 1 hour periods during which all identical instruments are operating and returning valid averages. M represents the number of identical sensors operated. So in a condition, in our case, say that we have 3 sensors in hand, then M is that particular number 3. Then you have XHG in this here, which is the 1 hour averaged PM concentration for that particular RH and sensor J. XH bar, which represents to the 1 hour. So this is average PM concentration for average across all the M sensors. That's average concentration. And X bar is the average PM concentration for the complete collocation period which you're considering. So this is simple formulas which you can use to look into the inter-unit precision among the devices. So to be noted here, till now we have not compared the sensor to a reference instrument. We are only looking into what is the precision across the sensors from a particular manufacturer or a particular batch. Now, comparison of sensors to reference instruments. Now, here what we are looking is, when you want to compare sensor to reference instrument means, in the say that you can just look at it with like a scatter plot. On your x-axis, say you have the value from your reference instrument, and on the y-axis, consider the values that is reported by your sensors. So now here you're looking into the sensor NO2 in ppbs and the reference NO2 in ppb, and you're just trying to plot the data and see. Ideally, it should be passing through the 1:1 line if it is highly correlated to each other. And then here we are just coloring these markers with temperature, which is in the case of NO2, which can be one of the meteorological factor which can affect its performance. So from this plot itself, we actually identify that the values, if when the temperature is very high, the sensor is reporting negative values, which is not which means that while even this temperature is very low or below 25, the values are almost in the 1:1 line. So this means that there is something additional corrections required in respect to the temperature of that particular location, which can improve the sensor performance. So these things you understand with the scatter plot. And of course, there are other factors like other metrics which you can consider, that is R, Pearson correlation R, then coefficient determination R square, and then you can calculate the slope, intercept, and this can be easily be done using NumPy's polyfit function, which you can use in the Python language. Then coming on to another is the error metrics. Few error metrics which you can consider is the root mean square error, then the normalized root mean square error, and the coefficient of variation in mean absolute error. So these are the formulas which has been used for the various error metrics. And using these formulas, we can actually look into the error values of how the comparison of sensor is with respect to reference instruments. So now, as I mentioned, I'll be talking about the target value. So USCPA generally uses these target values in the daily average, but we have considered that in a 15-minute as well as 1 hour average, and then we have come to this particular numbers which can be used to look into the sensor performance. So when we consider, say, PM 2.5, if you want to check the precision among the inter-unit devices for a batch, for PM 2.5, your R value should be greater than 0.9, R square should be greater than 0.8, a standard deviation less than 5 microgram per meter cube, and the CV value less than 30%. If this criteria is, if these 4 criteria are met by that particular batch of sensors, then we can say that the particular PM sensors in that particular batch is precise to each other. Now, when we want to look into the comparison of a PM sensor towards the particular reference instrument, then we consider the slope for bias, slope, and intercept. So the slope we consider 1 plus or minus 0.5. And for the intercept, if it is between -5 to 5 microgram per meter cube, then the linearity here we consider for R greater than or equal to 0.8, R square greater than 0.7. Then in the case of RMSE, less than or equal to 7 microgram per meter cube, Then for NRMSE and CVME, we consider less than or equal to 30%. So these are the different target metrics which we can use for comparing our sensors with the reference instruments. And this helps us to validate the performance of the sensors. So there are other, now if you see the NRMSE and CVME values, generally for all the pollutants, it is kept targeted as less than 30%. Then some differences when it comes to the different compounds is like, say you have when it comes to the coefficient of determination R square values for ozone, we consider the sensor performance is comparatively better. When you compare the sensor, comparatively works better when you compare it with the reference instrument, we consider a higher R square like 0.8 for ozone and CO, while 0.7 is considered for the rest of the other pollutants. So these are certain things which we can keep in mind while we want to look into the sensor performance. Now, based on these concepts that we have discussed, so we had recently published a guidance document for evaluating the performance and use of air quality sensors for the construction test or the PM10 monitoring. And this can be accessed from this link, which the PPT will be shared later. So you can access this guidance document and go through it. So here we have talked about the best sensor model. Like say you want to put a sensor in a construction site, whether you should be going with simple plant hour sensor, or should you be going with OPC sensors like the AlphaSense OPC, or which model that you need to use. So these things we have discussed. So ideally, our recommendation is that when you have to measure PM10, ideally go with an AlphaSense OPC R2 sensor. While when you have it, when you want to measure the PM2.5, you can go with the plant hours or similar kind of sensors which are commonly used, like Sensorion, plant hour, TerraSense, etc. And also, this guidance documents also looks into the how to carry out the collocation study. As I've explained, like what are the different metrics you need to consider, how you can calibrate the PM sensors, and how you can store the data and process the sensor data in the concept of PM10 and PM2.5. Now I'll move on to the next part, that is the data management system. So now we know that from the manufacturer API or from the dashboard, you can fetch the data. Now, once you fetch the raw data, what you do in a data management system or a data pipeline is you store that in first the whole raw data in a table, which is a row table. Now, this row table, what you have is like say that you for each manufacturer, you may have different ways in which you will have to consider this. That is, say that manufacturer 1 is reporting in UTC, manufacturer 2 is reporting in IST, manufacturer 3 is reporting in EST. So in different time zones, manufacturers are being reported. Then you consider a transform raw data table. This table, what it does is, it for each manufacturer, it will try to correct it for the standardized conditions. And then once that is done, it then pushes all the data in the standardized form to a standardized table. As I mentioned, this is the data standardization process where you have the 1 minute averaged data, which is having the correct units and correct parameter names at the same time in the local time zone. Once you have that, then you go to the aggregation stage. Say that you want 15-minute data or 1 hour data, you aggregate at this condition. Aggregate means averaging it out. And then you store it as an aggregated table. And then there comes the need for calibration. Say that you already have the data which is locally calibrated and you don't know to do any further corrections. In that condition, you just move at the table where there is all it doesn't require any calibrated table. Now here, this also happens when it is a reference instrument data. Say you have the BAM data or the gas analyzers data, reference data with you. You don't have to do further calibrations. So that data, you can store it directly to the calibrated table. But in the condition where you have to develop your own calibration models, apply the machine learning or model something which need to be corrected, then it moves to the application of machine learning models, and then it moves to the calibrated data table, and then comes back here. And then you have another check. Now you have the calibrated table, and it's not at this stage that we should stop. We should move ahead with one more step, that is applying quality checks. Sometimes your calibration can fail after a point of time. say that every calibrated table, sometimes you are applying just a linear regression, and someday you are getting a negative value for NO2. You do not want that to be there while you're analyzing your sensor data. Then you have to do this applying quality checks. And then you have a QC calibrated table, which can be used for further analysis. And if you want to, when you're operating a very big network, there will be multiple times that you need to identify any issues in the sensors. That if there are, say, higher values, which is beyond the threshold values being reported, which indicates that the sensor is dead, or if there are any other issues, you need certain alerts that need to come. So this can be pulled from different, either from the standardized table, which is just a row table, that is the complete sensor has gone bad, which indicates that sensor health is weak, or you say that the sensor is offline. These things can come as an alert, or say that at the calibration stage, your model has failed and you are getting complete negative values, then that need to be alerted. So this can be pulled out from these two tables. And then you can also attach the metadata to the device to understand, say that which location your sensor is, which is very easy because initially you will be dealing with the sensor device IDs, but after you put them in the site, then it becomes the location which you will be targeting. So this can be supplied with certain metadata, and the alerts can come along with the reports. Now, when we look at more into the quality checks, one of the useful thing is this alerts. So this is some we have developed our alert system in MS Teams. So what does this is, every 15 minutes we are getting alert about different sensors if there are any issues. So on 21st of October, that is the Diwali day in India, where you are having high concentrations of PM 2.5 being reported in the night due to the firecrackers. So what we noticed, a particular device ID in this particular location was reporting 432 microgram per meter cube of PM 2.5 in a 15-minute aggregated window. Now, during that particular day, a 432 is actually in a comparatively is something which is which you can consider as a valid point. But say on the same day, at a different time, that is 11:46 in the morning, another device ID is reporting a value of 3,159 microgram per meter cube for PM 2.5. This actually tells us that this is actually an invalid point, because this has already exceeded the, and this is the row value, that is from the row table or the 1 minute standardized table that we have pushed it. And this means that the sensor has gone bad, because the sensor was able to only detect 1,000 microgram per meter cube, but the sensor is reporting 3,000 microgram per meter cube, which means that sensor has gone bad. So these alert systems helps us to maintain a sensor network where you can differentiate between the valid data and then invalid data. So this helps us say we want to make the AQ data available in at neighborhood level. You can do it with alerts being carefully flagged. And for that, we have considered different thresholds or different alert systems that you have the this calibrated threshold alert, as I mentioned, from the calibrated table, you can consider it. Or you can say that sometimes some sensors, when it goes bad, they just continuously gives you the data. I mean, same number, say that CO value of 2 ppm is you are receiving it every day, continuously, every minute, the data just comes CO as 2 ppm. This means that there is a, like your initial one, even there is no change in the data throughout the day. So either these things you can look into. Then another thing you can look at, say there is no change in the maximum and minimum values over a day. Say that you have an RH, you need to look into the RH sensor, and the RH is not changing at all. While ideally it should be changing throughout a day. Like in the mornings, you should be having higher RH, afternoon should be lower RH, but there is no change at all. Then you can pull it from this particular alert. Another alert is that, say your sensor is offline or not transmitting data continuously. Say that you can keep some time interval which you want to look into. One of the thing is that, say, continuously 2 hours, the data is not being transmitted. One thing is that when you are transmitting data through this Wi-Fi or IoT, there are high chances that sometimes the network is not stable, the data is not being transmitted, but your sensor is active. In that cases, it's quite easy that, okay, the sensor, maybe after 15, 20 minutes or 1 hour, the sensor will come back. Once the network is back, the data will be pushed back. But in cases where the sensor is completely gone offline, the power is switched off, say that after 3-4 hours also you're not getting the data, that means you need to check into what has happened with that particular device. So this helps you with the sensor device status. Then there can be the average alerts, say that in 8 hours, in 1 hour, which you can look into. Depending on the user cases, you can make your own alert systems, which can help you with this data management. And we have actually developed one dashboard or a web app that is known as AirNet, which we are using currently for operating our sensor network in Bangalore, which I'll be walking you through that. I'll just go into that AirNet. I hope that you are able to see the AirNet login page.
Yes, we can see.
Yeah. Thank you. So here, this is airnet.cstep.in, where you can register and look into the data. So this is a web-based application which is providing the QSEED calibrated data for our Bangalore network. So here we have developed this such a way that you can register and you can register, or you can, this has a data control where you can specify what is the type of data you want to share with any other person who is logging into. Say that there is within our say the data we need to share only within our organization, say in CSTEP alone. Then in that case, we will be assigning in the particular category. Say that we want to share it with like a policy maker, or say that one sensor host needs to the access of particular data just for that particular location. Then in these conditions, we can uh, assign the different levels of users and then register here. So this is one advantage of this web app. I'll just log into it. So once you log in, you are coming onto the first page, which is the map. Here you have the Bangalore urban region, which is our current study location, and this is the Bangalore rural region. So currently our sensors are placed within the Bangalore urban, and the colors as you come, the colors that you see here first itself, it's the 1 hour average PM 2.5 for the last 1 hour. So here, say that I have a Asha Township, which is one of the locations. So here, consider that you have PM 2.5, PM 10. You have the different current values for the last 1 hour data. So this is what you see here. Then you can go to the graphs page, where you can see the last 24 hours. This is a simple time series. So this can help you to quickly identify what is the ranges, say what is the values that you're getting. So this is a simple dashboard which you can easily use for looking into your data, your network data. And then you have the table, and then you can come to another page, that is the network page. So in network page here, what it represents is whether this particular device was online or offline. Red represents here the offline and green is the online in the last 1 day. And then you have a table which can tell you the device location parameters, record the different record how much 1 minute standardized data was able to acquire in the last 1 day, and which is the device manufacturer considering. And there is an option here where you can actually change the parameter. Say that you are moving one location sensor from one location to another because you do not want to continue that particular location. You just wanted to change the device. Then here we have the edit option. So this web app actually gives that whatever in the backend, the metadata you want to change for the sensor, you can quickly change it here. And then it comes to the user management page, where you have different profiles. Like if it is an administrator role, it will be like administrator role means that you have access to the whole data set. And if it is just a sensor host, that is a single person you want to look into, then you have the dashboard of sensor host. Then comes to the data download page. And in data download page, you have two types of data available. One is the QC 15-minute calibrated data, which is just so any researcher who wants to look into this data, you can just click on the QC data and just get it. And suppose you want a data which is not QC but calibrated, then you have another option for row. but this is generally available only for the admins, because generally the researchers doesn't want to have a raw data when they already have a QC data in hand. And you can select whichever location you want to get it, for which date to which date, and in Excel format, in a 15-minute interval, the data will be available. So this is about our AirNet web app, which we have developed for looking into or for monitoring our sensor network in Bangalore. Now, yeah. So I'll just come back. 1 second. So, which is are you able to see the screen for my PPT, or?
We can see your PPT, and then
Okay,
I
fine.
just
Okay,
have
cool.
one question before we go to the next slide. So is this data that you're collecting in Bangalore is open for the public to look how is the equality trend in the urban Bangalore?
So currently, with the login access, you can, so that we can see that it is not being like, we would like to keep a count on who is accessing the data. So we have kept,
Okay.
that's why we have put at the registration page, so that we know like this person has access to this particular data.
Mhm.
Because so we do not want to have it like anyone can access and any issues coming up in the end. So that's why that
Okay.
user page is there. Yeah. So
Yeah,
now
and
suppose
one more question.
yeah, sure.
Yeah, just because you're talking for a long time, I just thought. So one more question from my side is, so where are these sensors placed? Is it on the residential homes or on the government offices? So where are those sensors placed in Bangalore?
So these sensors, like we have representation from residential areas, then from curbside, then industrial area. So it's like a mix.
Okay.
It's not just, and also it is like we have placed the sensors in at a height of 2 to 10 meters, considering the human breathing level. And
Mm-hmm.
we are looking into whether, say that you have a metro construction area, and do you is it there that the high concentrations are coming? So we have just put a mix of
Okay.
site categories.
Okay. Thank you.
Okay. So now, once you know that, you can the next question is whether we can develop the data management system of our own. And currently, CSTEP has actually released the open source codes for developing your own data management system if you want to do it for your location. So here, what we do is we have actually uh, the codes are available in the GitHub repository, and I'll be walking you through the repository in a short time. Before that, let me just walk you through the flowchart of our data management system. So as I mentioned, we load the manufacturer configurations and store the raw data. Then for each manufacturer, we do a pre-processing, which is for correcting the column names and the correcting the units and the time zones for each manufacturer, which is a staging table. Then we come on to the standardizing session, where we are loading the table to a particular schema, and then we insert into the standardized table. So we can for the whole that from the stage where you have the different manufacturers separate tables, we reach a table where we can different for the whole network, you come to a standardized table. Then you aggregate it or average it, as I mentioned earlier. And then you can consider for the non-calibration table, I mean the non-calibration task, that is, say you are having reference instruments or it's already calibrated data, then you don't need to go for calibration. Then you can jump to the calibrated data 15-minute table, or you can go to the calibration, where you apply your machine learning models for correcting your sensors, and then you do the quality check. And also in our open source codes, we have also given open source. We have also put up the codes for visualization using the Apache superset. So now I'll just move on to the I'll just move on to the GitHub repository. I hope that the GitHub repository is visible.
Yes, we can see.
Yeah. Okay. Cool.
Yeah.
Yeah. So here, github.com CSTEP Bangalore AQDMS is our GitHub repository. And then here you can go to the README file. We are using an Apache 2.0 license. And when you go to the readme.md file, here we are giving the prerequisites that is required for developing your own data management system. So this codes actually covers how you can ingest data from multiple sensor manufacturers via their API. So we have actually given the codes for the few Indian manufacturers. The API clients are already developed. Then we standardize and aggregate the data, then applying the different calibration models and performing quality checks. And how do we store the data in a database? And finally visualize in an open source like Apache Superset. How do you can do it? So this is how we have done it. And then this README file, if you go, you can see the prerequisites required. How do you set up your environment? Then what is the project structure? This is somewhat a data engineering part of our air quality data management system. Then you have the pipeline overview configuration, using how you can use the data pipeline, and how do you initialize your database. Additionally, we have also given some machine learning calibration models, which as an example, along with certain examples of data, which you can work out as a trial for developing your calibration model. But important thing to be noted is this is these calibration models which we have considered here are just for a demo purpose. So if you want to build your own calibration models, please do collocate your sensor with reference instrument and build it, and consider this as only an example to just check whether your database management system is actually working. Then when you go to this folder, here you have the different airflow configurations, because which are required for different manufacturers, we have mentioned here. Then for the data visualization part, you have another visualization README. So here, how you can create your own dashboard using the Apache Superset is also the given in detail here. So you can use these steps to create your own dashboard. You can for your own network, you can manage your data and create your dashboard. So now I'm coming back to my PPT. Yeah. So so all this has been developed with a strong support from my past and current colleagues in CSTEP. Like it's a teamwork that has led us to the development of this air quality data management system particularly for the sensor networks. So I thank all my teammates who have worked with me for this. And this is like we were funded by Google Rainmat and Coefficient Giving, which is formerly known as the Open Philanthropy. So we were supported by these funders also for the development of this AQDMS. So if you have any like in detail queries which you want regarding how you put up the AQDMS, how you develop it and all, please do write to us. I have given my mail ID as well as our common mail ID, which you can look into. And also, I invite everyone to look into the guidance document which we have published. And also, I would like to give you just inform you that so our first phase sensor evaluations reports will be released by this month end, wherein we'll be talking about how can you develop your calibration models for different pollutants like PM2.5, PM10, NO2, and ozone. So please stay tuned to CSTEP page. You can expect the report to be released by this month end. And these are some references which you can go through for looking into the sensors data performances. I'll invite everyone to look into particularly the Schneider et al., where you look into the different data levels for processing, and our GitHub repository and our guidance document, which can guide you through. Yeah. Thank you, everyone. Yeah, now I'm open to questions.
Yeah, thank you so much for this wonderful presentation on showing us the different guidance document and also walking us through the data management system that you have developed. I think there are like a lot of materials out here for the participants also to look into to develop their own data management system. So since we have some time, I would request the participants to unmute yourself and ask any questions that you have for him. Any specific questions? Okay, so I have one question on this. Like you mentioned at the end, also during your presentation, that you're going to publish a report which have looked at the sensor performance, and so can you explain more on that? Like, what are all the factors that were like? What are the factors that you considered for the sensor evaluation? And also, is it something on conducted on your calibration side, or something on the ambient environment, or the construction side? How was that done? Can you give us some more information on the upcoming publication from your group?
Okay. So the upcoming publication is based on a short and medium term evaluation of five sensor integrators that is available in the Indian market. So as I mentioned, we had two phases of sensor evaluation. One was a long term 1 year, and another one is a short term 4 months. So this is the results from the half of the phase one. So it's a short and medium term, like you're considering 6 months of data and looking into it. So the parameters were pollutants which we consider were PM 2.5, PM10, NO2, and ozone. And then what we had sensor like 5 to 25 sensors from each manufacturer. So minimum you have in hand at least 5 sensors to compare the precision among the sensors. So we use the same metrics that I mentioned earlier, like you have the R, R square, SD, CV. These metrics we use for the inter-unit precisions. Then we try to plot the pair plot, see how the performance is. And then we compare this these sensors which with each reference instrument which we had, and then we look into how the performance is with respect to the different metrics that I mentioned earlier. So that is the one part, and we were looking into three different levels of data at that stage. One was that the raw data in voltages that you get, how the voltage response is towards the reference instrument. Is it linear, or is it non-linear response that you're getting? So that was the first level of data which we looked. The second level of data which we looked is, say you have a manufacturer factory calibration is applied. So then when the factory calibration is applied, how the performance has changed with a simple factory calibration. And the for the third data set that we looked at, we developed our own calibration model, and then we looked into the performance of it. So because our own calibration model means we are applying the local conditions to it. Once you apply the local conditions, ideally your sensor performance should start improving. And how did it improve over the time? So that was, or do you find that certain models work only on particular time, and then over another time you need to go with another model? So we developed actually five different algorithms mainly for each device, like so that you have linear regression, quadratic regression, then the machine learning models, random forest, XGBoost, support vector regression. So these five models we looked into and see which is the best performing model for each particular device. And at the same time, we also looked into whether for a single manufacturer, can you come up with a single particular model, a single generalized model for each manufacturer. So say that I have five devices from, say, manufacturer A. Can I have just a single model apply across all the five if the sensors are precise? If it is not precise, then it's a different question. So that was one thing which we looked. At the same time, we also looked into whether one particular device requires, say that if each of the, say, five manufacturers you have, five devices you have, does each device need but a single model even when you the precision across the devices are good? So these were the things which we looked into, and the results of this is what we'll be publishing soon. And then coming on to the guidance document, The guidance document we have developed based on our 1-year analysis of the PM sensors. So we had different the main the sensor models which we considered was Plant Tower, then TerraSense, Sensorion, and AlphaSense. OPC, AlphaSense OPC. So these are the commonly used sensors. So we looked into whether how the performance of each of these sensors is under different conditions. When you're in a construction site, ideally your PM 2.5 to PM 2.5 by PM10 ratio will be lesser than 0.4. So whether a particular sensor works fine in these particular conditions. And if it is not, then ideally what you're doing is sometimes you are underestimating your construction dust. So putting the exact sensor model is required even when you have you can build so many calibration models, but if your sensors raw values are not responding to your actual context, then things change. So this was something which we looked into, and our guidance documents in detail talks about that.
Thank you, Emil. We have one question from Victor. So, as you mentioned, like a lot of sensor names. So, is there any best sensor that you recommend to install? And we saw your plot for Bangalore, like you have different sensor getting in was installed in different places. So, how was those sensor installed? Is there any criteria that you had based on population or based on area? Like, was there any criteria that was set up to install those sensor in this network? Victor, was my question correct? Would you like to unmute yourself and ask if you have any further? Okay, I think
Okay.
he's not.
Yeah. So when it comes to the choice of sensors that we have put up in, like there is a mix of manufacturers currently, because when you say sensor manufacturer, actually they have, in short, they are using actually the actual measuring sensor. Sometimes it's almost the same. In the Indian context itself, there are you have different names, Respira, you have AuraSure, Aeron, but sometimes all of them are using the same sensor inside. Say that they are using a Plant Tower 5003 series, then it makes that just you need to evaluate the 5000 actual Plant Tower 5003 is the main thing. It's not the integrator but integrator plays a role when it comes to data management. Whether are you able to get the data on time? Is the real-time data available for your purposes? That was one thing which we considered. Like, main thing was our network itself we developed based on a like check to see how the different manufacturers can provide the data, because inside it is almost a majority of them are using the same. Majority of the manufacturers right now use AlphaSense electrochemical sensors for gas measurements. Few users EC-Sense gas sensors, but over time, over our evaluation, we have noticed that EC-Sense doesn't give much, like it doesn't performs well on a higher concentration, because we have noticed that sometimes EC-Sense just reports below 17 ppb of NO2 in the case of NO2. And in India, if you consider NO2 17 ppb means it's like you are missing the major part of it. So that was something which we noticed. So when we notice such issues, then we talk to the manufacturer. We help the manufacturer to find which is the best, and then we advise the manufacturer to have it changed to the sensor which is useful. So that was something which we tried with our network. So if nearby locate like the way we put the sensor network was that not one manufacturer is near to the next. So you can have a cross checks, and then in between you bring the sensor back to the collocation site, our IndiSet facility, to check the performance of the sensor in between, so that you know that the sensor is not and sensor is performing well, even in over time it is able to perform. So these are different ways we try to make sure that the network is able to capture the proper data.
On the area and population, like how was
So
those?
placing of the network sensors,
Yeah.
right? Yeah. So when it comes to the placing of the sensor, the way we designed our sensor network is mainly we looked into satellite data. So our consideration was, say you have the MODIS AOD data and the Tropomi NO2 data, which we considered as a base for our network design. So we averaged it for the previous years, that is 2021 data, we averaged it. And then we tried to divide our study region into 1 kilometer by 1 kilometer grids. So now you have the whole Bangalore, which is approximately, I think, 2,200 square kilometers, divided into 1 kilometer by 1 kilometers grids. And then you apply your AOD value and your NO2 value, satellite data to it. Now what we did is we divided the values into 10 percentiles so that each grid represents a particular percentile. Now from each percentile, we selected few locations which can be a which can come as a representation of particular concentration. So then it is like you are just with the satellite data in space. So you know that certain locations will have high concentrations, certain locations may have lower concentrations, and that was the base in which we started working with. So right now we are in a process to check back if whatever we assumed that it is higher and lower, is it the same that we are getting? So right now we are in a process to check back the data after the whole 1 year. So we are now looking into whether the satellite data and our conclusions are coming. So that's the next step we are working on. And when it comes to population, it's a majority of the thing which we noticed, the higher concentration as per satellite data, it was in the BBMP area. So that's the main reason also, like that is BBMP is the corporation area, so that it's within where more things happen. Rest it's like an outer area that you see in the Bangalore urban. So that's where more people are there and where you see that more open burning happens. So more things are happening in that area. So that's where we mainly focused on.
Thank you so much, Emil. And Abdul has a question which is not clear to me. So Abdul, can you unmute yourself and ask the question? Or the question is this. So does everybody has to test the sensors as per the conditions or the area that we are? So I'm not clear. Like, does he mean that? I think as the question is, does everybody need to undergo calibration or for a sensor, or is there any recommended ones that you prefer which does not require? Yes, try different
Right.
sensors. Yeah.
Yeah, I
Uh,
think maybe like for each condition, do we need a test to identify which sensor? Is
yes.
that what I think?
Yeah.
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 So I would say that right now, do everybody have to try and test different sensors? Yeah, that's a question. Yeah. So right now, if you look at the different performance of sensors, I mean, there are websites where you can get the sensor performances. So one is this AQ Spec, the South Coast AQMD's AQ Spec website. If you just go, you can get the sensor evaluation report for majority of the sensors, because they are being then that is one of the thing that so that is the US perspective you will get. Then the another thing is this AfriSet website also, you have the reports on different sensor performance. Then in the Indian context, currently we are working on it. And then we have also this AirLab micro sensor challenge which we are partner. So here in this particular challenge, in 3 locations, that is AfriSet, where you AfriSet in Ghana, where you can have the Harmattan episodes happening, and then you have the in Paris, Air Paris. So in the European conditions, then the Indian conditions right now. So the South Asian context you can look into with our reference. So, and here currently in India, we have been evaluating 18 different manufacturers already. So that and it is from 11 different countries manufacturers. So you have so you can actually once the report will be released by September for this the current evaluation which we are currently doing. So so from these reports you can identify some similarity, like say your environment is similar, then you can have a rough idea that okay, maybe this sensor can work well for me. That is one thing. But within India itself, if you see, the when the pollution level changes or when the meteorology changes, things actually change. Say that the condition in Bangalore might not be the condition in Delhi, might not be the condition in Rajasthan. It's not the same chemical composition or the weather parameter in Kolkata. So it's like in different parts of India itself, there are changes. So what you need is that at least to have a 15 days of collocation is something which we would say as a, like, that will be the most advisable condition that you can be sure of what your performance is. Because blindly, if you take the sensor, it is in a different environment. Sometimes this factory calibrations even happen inside a lab. It's like an air conditioned room. You are checking the precision of the devices, doing a simple calibrations. But that might not be the performance when you put that particular sensor in the outdoor conditions where you have high temperatures going, higher RH coming, lower RH coming. So things will change. So advisable is always to have a check, at least say 15 days, compare it with a reference instrument, see whether the sensor performs well. Then you can be a better, more sure. That's a way you can improve the data reliability of your sensors, I would say.
Thank you, Emil. And we have one question from Oluwal, like, is this data available public? So you have already mentioned
Yeah,
there is we have to
you can
bypass
register.
regular to
Yeah.
maybe my question is there any plan to make it available to public, either sharing it in platforms like OpenAQ, or because a lot of low cost sensor they share the data with OpenAQ and so do you have any plans in future where this data will be made available for public?
So we are in discussion with the government bodies also for this because, as you know, in India, when it comes to local sensor data, we have that it should not be used for any regulatory purposes, local sensor data, because of this issues in the data reliability itself. So we are in discussions with the government bodies on how we can bring it. So, but I would say that this stage, we have to be cautious about it. That's the main reason itself that we are trying to build the trust in the sensor data using all these data management systems where you know exactly what you have to flag, whether it's so that you do not go tell that, okay, my community, I'm getting 2000 microgram per meter cube of PM 2.5 because my sensor showed it. We do not want to have that. So that's a main. So, but if it is properly flagged in your neighborhood level, yeah, we can. But that's a something which we are in process. Currently, you'll have to register.
Yeah, thank you. I was just registering to the platform and I gave I'm resident of Bangalore, so I wanted to know, but yeah, maybe that is not an right reason to specify
Yeah,
here.
the team has to approve it. It
Yeah.
goes.
Yeah. Thank you so much, Emil, for your wonderful presentation. I think we'll have so many questions once we start exploring the resources that you have
Yeah,
shared, even the GitHub libraries. I think those are all useful resources. So maybe we will have some more questions once we start looking at the codes. And yeah, thank you so much for joining us today. And we'll make the presentation available on our website, and even the recordings will be made available for everyone. Thank you all for joining us today. Have a nice bye bye. Thank you.
yeah. Thank you.